everyone. Sorry for the weird stopping points in here. I think I figured out my issue with videos, so they should be uploading completely from here on out. Okay, so we were looking at the following, where I said that we could set up this equation and use lambda 1, our eigenvalue, and x1 vector, which is our eigenvector. But I wanted to talk a little bit about notation on this first. For the notation on this, what might make sense to some of you is if I wanted to talk about my first eigenvector, let's say it's a 2 by 2, I might label these 1, 1, and then 1, 2, or something like that. Or maybe 1, 2, and 2, 1. And then my second eigenvector I might call x1, 2, and x2, 2. And this makes some kind of sense since you have your first and second eigenvector and you want to match these somehow. But this, to me, looks too much like a matrix, like the entries of a 2 by 2 matrix, and there's really no good combination to use that's going to let you know what entries I'm talking about specifically. And your book agrees with this. Your book says that this form is a little bit too messy. Right? It's too messy to have these multiple ones. So what we're going to do instead is we're going to call x1 vector, we're going to call that x1 and x2 for those two entries, and then x2 vector we're also going to call x1 and x2. They're exactly the same, right? But as long as we keep in mind that we're either working with the first eigenvector or working with the second eigenvector, then it shouldn't be a problem. We'll just be able to keep in our heads and we'll know which entries we're talking about. It won't cause any issues unless we try to solve both at the same time or something like that. So anyway, that's the notation we're going to use. Continuing with these, we have a minus lambda I1, and we actually already figured this out in the previous matrix. So we have A is going to be 2, 1, sorry, it's been so long, I need to remember what this is. Okay, 1, 2, 2, 1. Minus lambda, right? So 1, 2, 2, 1. And then when we subtract lambda 1, which is 3, minus I, that means that these two entries are going to be minus 3. So 1 minus lambda, and then these are each minus 0. Okay, so I get negative 2, 2, 2, and negative 2 for my entries. When you get it to this point here, you've got one matrix times a vector is equal to another vector. So the way that I like to do this is to think about this as an augmented matrix problem, but you can also think of this as being a system of equations. So I'll show both of them, and it'll be up to you to pick which one you like to use. Right. So just filling in what these two vectors are. The problem looks like this, and one way that I can split this up is to, over on the left-hand side, I can do matrix multiplication. So this is negative 2 times x1 plus 2 times x2 is equal to 0. And then for the bottom entry, that's going to be 2 times x1 minus 2 times x2 So this times this and this times this is going to be equal to 0. And what I end up with is a system of equations that I can solve for x1 and x2. This little shortcut, or kind of a handy way to represent everything here, is if you have matrix, vector, vector, then we get -2, 2, 2, -2, and 0, 0 on the side there. So either way, our goal is going to be to solve for x1 and x2. And since we're working with the first eigenvector here, that means that's going to give us the entries for our first eigenvector. Okay, so I'm going to work with this idea over here, but just know that these two ideas are equivalent, right? I might ask you to work in between this type of form and this type of form. Let's use that form on the right. And we get -2, 2, 2, -2, and 0, 0. Like I said in the previous video, I'm not going to show every single step for this one. I think that in linear algebra, you've probably done plenty of this, so I won't be writing individual steps like row 2 minus row 1 becomes row 1, things like that. I'm just going to assume that you've done this enough and do them in real time. The first thing I'll do is I'm going to take this row and add it to this row. So get -2, 2, 0, and 0, 0, 0. And then I can divide both of these by 1. So I'm going to get -1, 1, 0. Sorry, divide by 2. That's what I said. And what this is telling me is that I've got two equations now. So the top equation here, that says that -x1 plus x2, so sort of, right, to be really clear, -1 times x1 plus 1 times x2 is equal to 0. And then this bottom equation here is that 0 times x1 plus 0 times x2 is equal to 0. Now, this first equation here is going to give me x1 is equal to x2, right? And then this next one is going to give me that 0 is equal to 0. I'm going to work with this one on the right-hand side first and say that this equation offers us a degree of freedom. What that means is the freedom that we have is we have the freedom to choose what one of these variables is going to be. Since we are looking at this and 0 equals 0, that's going to be true regardless of what x1 or x2 is. So if we view this as a system of equations, all we need to know is that x1 is equal to x2. That's the only constraint that we have. So we'll say this allows us not to choose one variable. We'll say the value of one variable. Either x1 or x2. And since we get to choose what it is, we'll say common choices common choices are 0 and 1. And then very rarely we could choose I. We'll see that in section 4.7, I think. But yeah, usually you want to choose them in this order: 0 if you can, and then if that's not available, 1, and if that's not available, I. So in this case, if we wanted to choose 0 for this, then x1 would be 0, and x2 would be 0, and then our eigenvector would be 0, 0. So we don't want that. Right? We don't want an eigenvector of 0, 0, since that's a what we call a trivial solution to this. So I'll say that since x1 cannot equal 0, we choose x1 is equal to 1. So we'll just set that equal to 1. By the way, just by convention, I'm always going to choose the value of x1 over choosing the value of x2. That just makes one less decision that you have to make. So if you're following along, that's what I'll be doing. Okay, so we chose x1 is equal to 1. So that means that x1 is equal to 1. So that means that x2 is also equal to 1. And overall, what that means is that my first eigenvector is going to be equal to 1, 1. Right? x1 is equal to 1, 1. x2 is equal to 1. Okay. So that's our first eigenvector. This is a pretty standard question for showing what's going to happen with finding eigenvalues and eigenvectors. So the next one that I'm going to do it just a little bit quicker, but it's going to be the exact same idea. We're going to use this second eigenvalue, -1, to find our second eigenvector, and let's see what that looks like. So we set up this equation. This is our eigenvector finding equation, and this is going to mean that let's see, so we had 1, 2, 2, 1, but this time is we have -1 for our eigenvalues, so it's going to be -1 or +1 in this case. So just skipping right ahead to the augmented matrix, it's going to look like this. Hopefully you can handle this one. Something I neglected to mention in the last one was that you know, ideally when you're doing these problems, you'll end up with an identity matrix here. So 1, 0, 0, 1, and if that's the case, then that'll just tell you, hey, x1 is equal to 3, whatever's here, and then x2 is equal to 7, whatever the entry is here. Oftentimes that's not going to happen here, but rather than having a goal of getting the identity matrix here, we should maybe have a goal of just getting as many 1s and 0s as we can in this matrix. So first thing I'll do is just subtract this one from the second one. And then I'll divide this one on the bottom here by 2. This top row is going to give me a degree of freedom. And this one at the bottom here is going to be that x1, so 1 times x1 plus 1 times x2 is equal to 0. So that's going to mean that x1 is equal to negative x2. Since we have a degree of freedom here, this means that we're going to be able to choose what x1 is equal to. So we can choose x1 is equal to, well, 0 is not a good choice because then we'll get 0 and negative 0. So let's choose x1 is equal to 1. And if x1, let's see, we have x1 is equal to negative x2. So that means that x2 has to be equal to negative 1. So our second eigenvector is going to be 1, negative 1, just like that. Now that we have that decided, we can gather up all of our information. So we have eigenvalues and eigenvectors. In this video, I haven't yet covered how this applies to differential equations. I just want you to have a resource to see what the linear algebra looks like in these problems. But when we get to actually solving differential equations, as long as you can find eigenvalues and eigenvectors, there's not a whole lot on top of that that you need to know how to do. This is, again, mostly algebra with some linear algebra thrown in there. Okay, so just as a preview of what this will look like when we start solving differential equations, the type of differential equations that we're going to be solving look like this. So we'll have a y prime vector is equal to some matrix times a y vector. And our solutions to this differential equation system they're always going to be a vector. So we'll, just like when we solve for y in chapter 2, we're going to solve for y vector here. And the form that they're going to take sometimes, again, if we have repeated eigenvalues or complex eigenvalues, we'll look at different variations on this theme. But y, the solution vector is going to be c1 e to the lambda 1t times the first eigenvector plus c2 e to the second eigenvalue t times the second eigenvector. So it looks really similar to chapter 2, e to the lambda t. Only thing we're adding here is this extra eigenvector. So, review this video, and if you know how to do finding of eigenvalues and eigenvectors in here, then you're going to be in really good shape for the rest of this chapter. All right, good luck with your studying, and I'll be posting a new video shortly.